Today we'll be solving exponential equations with common bases. So if we want to rewrite each pair of numbers so that they have common bases, we need to refer to our perfect roots table. Let's consider the values 8 and 32. We want to rewrite these values as terms involving an exponent where those terms have the same base. Okay. If I look at my perfect roots table and I want to find somewhere on there the number 8, okay, I can find it in the perfect cubes column. To rewrite 8 as an exponential value, I can write 2 times itself 3 times, or 2 cubed, and I could get 8. I now have a base of 2. I want to write my second value, 32, as a base of 2. So in my perfect roots table, if I go to the number 2 on the way left side, in that row, I want to go to the right until I see the value 32. And I can go all the way to the right in that last column. That's our fifth power. 2 to the fifth power is 32. They now have a common base. Their base is now 2. 2 to the third is 8. 2 to the fifth is 32. They have the same base. Our next example, 3 and 81. I want to write these values as terms with the same base raised to some exponents. Well, I can't manipulate the value 3, so that's going to stay 3 to the first. There is no whole number when I raise it to an exponent, sorry, not cube it. When I raise it to an exponent, that gives me 3. So 3 to the first power is going to be our first term. Well, can I rewrite 81 with a base of 3? Go to the row that starts with the value 3 on the way left on your perfect square or your perfect roots table. Go all the way to the right, not quite all the way, over to the fourth power column, and it's 81. 3 to the fourth power is 81. Those now have a common base of 3. Here's our last example involving just constants. If I go to my perfect roots table, 25 and 125 are in the same row where their base, common base, would be 5. 25 would be 5 squared. If I go to the next column, 5 to the third power is 125. Those now have a common base of 5. Our last kind of meticulous example involving fractions. If you remember back to our negative exponent rule, a value to a negative exponent introduces a fraction. So 1/7 would be the same as 7 to the negative first power. Remember that the sign switches and it goes to the opposite side of our fraction bar. So a lot of times when I had 7 to the negative first power, I would go like this, change the sign, and then I would just write that it goes down. So I now have 1/7. So I rewrote 1/7 as 7 to the negative first power. I want to see if I can rewrite 49 as a base of 7. Well, that one's pretty simple. 7 squared is 49. Those now have a common base of 7. This is handy because if you see a variable in the exponents, we want to try to get those terms to have same bases and then set the exponents equal to each other. This is called the method of common bases. I say if possible. We'll discuss in a further lecture if it's not possible to get a common base. For all these examples, it will be possible. So our first example, we want to solve for x. Okay, the previous slide said that I want to get a common base. Well, I have a common base. They are both 5. The next step said I could set the exponents equal to each other to solve for x. Well, there is no further step to solve for x. X is now 4. If I plug 4 in for x, those terms are now equal. So I have solved for x. X is equal to 4. Our next example, I've got 4 to the x equals 8. I want to rewrite those constants as the same base. Well, a row that has both a 4 and an 8 in it, I can rewrite those with a base of 2. Well, 4 is, so 4, that's just 2 squared. Okay, I'm just going to bring this x value along for the ride. So I had 4 to the x, that is now 2 to the 2x power. I can rewrite 8 as 2 cubed. Now that I've got the same base, I can set the exponents equal. 2x equals 3. If I were to divide by 2, I now get x equals 3 halves. Example 3, and we'll do one more after this one. I've got 3 to the x plus 2 equals 9 to the x. Well, if you remember in our values, or our examples that had just constants, we can't change 3. Okay, I can't manipulate 3. So I'm going to keep the base of 3 on the left side. I want to change 9 to a base of 3. Well, 9 is 3 squared. So my left side stays the same. I can rewrite 9 as 3 squared. Okay, and I just tack this x right next to, I bring it with, right next to that new value in the exponent. And those are being multiplied together, 2 times x, that's in the exponent. Well, I've got a same base. Okay, I've got the same base. They're both a 3, so I can now set the exponents equal to each other. In order to solve. That's the method of common bases. Well, I just bring my x plus 2 and my 2x down and solve. Well, I want to get the x's on one side and the constants on the other, so I'm going to subtract x from both sides. So x equals 2. Okay, 2x minus x is just a 1x, and I had a constant of 2 left. So my solution, x equals 2. Here's our last example for the day. Again, I want to rewrite these constant values, okay, as a same base term. Find a row on our perfect roots table that has 81 and 27 in it. Okay, a base of 3 raised to some power, I can get both 27 and 81. So I know my new base is going to be 3. 3 to the 4th power is 81. Okay. 3 to the 3rd power is 27. One thing I want you to notice, that 4th power, that's being multiplied by that entire previous exponent. Okay, I'm multiplying that 4 times x plus 2. And the same thing is happening here. I'm multiplying that 3 times 5x plus 4. Well, when I bring those things down, I need to distribute. That's what I'll get for my answer, but I want to show you what happens when I distribute. I get 4x plus 8 equals 3 times 5 is 15x plus 12. I'm going to get the x's to the right side. And my constants to the left side. Okay, I'm going to go over here. I would get negative 4 equals 11x. I can divide by 11, and x gives me negative 4 over 11. Okay. I just want to remind you our steps. Okay, first would be get the same base. Oops. From there, I can set the exponents equal to each other. And my third step would be to solve for x, or solve for your variable using the inverse order of operations. See you later.